bring academia as well as the startup space, who are going to bring some pretty diverse perspectives. Two of them have Switzerland connections, but you still have to be provocative, right? So that's the rule. Don't be neutral, is what I was going to say. All right. With that, the speakers will all give short opening remarks, maybe 10 minutes or so. Maybe we'll start with Torsten from ETH and take about 30 seconds or so to introduce yourself and give the context to your comments. Thank you. Is your mic on?
Oh, I guess this mic is not on. Yeah. Okay, so yes, I'm Torsten. I'm from ETH Zurich, from Switzerland. I'm not going to be neutral. I mean, how could you even, this is no. I mean, the two people you have from Switzerland here couldn't be more non-neutral than they could have chosen. So I would not be worried about this. So we'll see. But this is going to be disappointing. So I'm going to give you a little overview, and at the end, there's going to be a lot of disappointment. So please bear with me. But to soothe this a little bit, this disappointment, I want to start with an XKCD. It's always good to set the stage so you can have something to relate to. So if you look at this, this is actually something that I'm going to go into a little bit more detail on this business here. So fields arranged by purity. So what does that mean? So sociologists are the least pure in that XKCD comics, and mathematics is the most pure in some sense. So of course that is slightly offensive. I didn't make this, so don't blame me for this. I want to do something else. I want to arrange AI methods and scientific questions, because at the end we are at the meeting that's called scientific foundation models along this similar axis. And the axis is ranging from empirical sciences to theoretical sciences. And what does that mean? So an empirical science is a science that is largely uncompressible knowledge, in my view. So that means this is knowledge that I cannot easily represent with a small equational basis. And then theoretical sciences is the opposite, obviously. So for example, uncompressible knowledge is medicine, clinical practice guidelines, PubMed. So all of these experiments, we have inserted some material into human, see how the human reacted, human died or bad, human got better, much better. And then this was all written down in empirical observations. Sociology is one of those, actually. I mean, it's not necessarily with inserting materials, but it's about studying very complex systems that is really, really hard to compress into small equations. But then on the other side, theory, like mathematics, is extremely compressible knowledge. So we can express this with a very compact form. And many of these compact forms that we've seen actually gained people Nobel Prizes, gained people the highest reputation in the scientific field, for example, the Navier-Stokes equation. And many of these other equations you probably know. And so now we can place each science along this axis, from medical diagnostics, biomechanical analysis, and then weather forecasting and climate prediction. This is something that I'm working in. So weather forecasting and climate prediction is somewhere in the middle. That has some component that is actually really well understood, but then there are also subgrid effects and things that are simply not modeled that you don't understand. So it's a mix between empirical sciences and compressible or theoretical sciences. Then, of course, structural mechanics is way further to the right, even though I had an argument yesterday with our panel chair. So we can argue that, and we're going to continue that argument. But now, what's the role of AI here? This is just a classification of compressible versus non-compressible. AI basically, going to the uncompressible knowledge, means that we can improve capabilities. So what does that mean? We can build complex models to capture more complex knowledge. And this is exactly what we are doing. And I'm going to give you an example in a minute. And that usually is built using data-driven representations. If you go to the right side now, what we do, we actually have the ground truth if we assume these models are right. So that's kind of stupid. We don't need complex models, or we don't need improved capabilities. What we need is to make this faster, because usually those equations are too complicated to be solved. For example, Navier-Stokes equation needs very, very fine grids to even work in most cases. So for weather and climate simulation, you cannot have very fine grids for the whole planet, obviously. That's a problem. So, and then on the right side, we use model-driven representations that have, by model, I mean scientific model in this case, so not AI model. This is a little bit of confusion here. So now if you look at this, somehow on the left side is what traditional machine learning has been doing for the last decades, improve these, what I would call uncompressible knowledge fields, and make them more accessible, like classification, regression, all of that, where we do not understand the equations. The moment we understand the equation, we dropped classical machine learning and we went by the equation. That's called scientific computing. And now that was used in traditional modeling and simulation. And now AI for science is converging those two fields somehow, or promises to do this. So we'll see how that goes. But let me look at an example on the left side. So for the uncompressible knowledge, medicine. one of the most important fields in our society. We all want to live longest, as long as we can. And medicine helps us to extend our lifespan and to make our life quality better, as we all know. So there are lots of benchmarks that we can go with. They're all publicly available. I don't want to go into too much detail, but what turns out is that these large language models, as we have them today, so-called foundation models, are actually extremely powerful in that respect because they have read the whole internet, they know all of this, and so they can answer these questions. The question is now, are these benchmarks that we looked at, these medical, MedQA and I don't know what, are those good benchmarks to assess the real capability of human doctors? No, they're not. But then there was a very interesting study that I just want to briefly highlight. I was not involved in this, that looked at how medical AI models actually perform in real settings. And so here you can read this if you want. I just want to summarize this. But what actually happens is very shocking in this study. In this study, it turns out that this is a score here, IDEA score. It's basically the model and the human doctor, they're competing in this test. They're presented in a scenario. So people walk in my hospital, guy is blue, doesn't breathe, is kind of half dead. What do? And then another set of doctors looks through this and grades what these AI models or the doctors did. And this is the IDEA score. The higher, the better. It turns out that the winner is O1 preview. The second is GPT-4. And then the real physicians are way behind. So the real physicians are significantly worse in the eye of other real physicians, right? That's the interesting thing. So the human oversight marks the AI models better than the actual humans. And it's even worse if you look at this other score. These are landmark diagnostic cases. It's a similar thing. You get a score by a human based on your proposed treatment, based on the inputs. If you only use O1 preview or GPT-4, it's strictly better than if you pair a physician with GPT-4. So meaning adding a real doctor to the mix makes the model worse. Right? So that's something to think about. And then the physician with other resources even slightly worse. So the model is still better. I mean, if you want a doctor in the mix, well, you get to deal with a slightly worse treatment. But at least you have the good fuzzy feeling that you have somebody responsible for what you're doing, for what is being done to you, basically. But now, the other side, the equations. So we now have already figured out that these models are pretty good at this, but now let's look at the equations. The equations are ground truth. That's at least what we are claiming. Well, until somebody proves that the assumption was wrong. So I always say that a Nobel Prize is given for inventing a new hypothesis, for example, the Bohr atom model, atoms are unsplittable. And then another Nobel Prize is given for disproving the previous hypothesis, saying, oh no, there are quarks and gluons and things, and then we split those elements. So it's not really clear. We have current assumptions, and we assume that these equations are right. But now if we assume this, the funny thing is, actually, computers already had superhuman performance since decades. So computers are much better at predicting the weather than any human is since a very long time because we understand these foundational physics. And this is just an example of too complicated to explain in my 12 minutes. But what we do is we run this by high-performance computing. There's actually an international competition, the Gordon Bell Prize, which my team and I'm a member of a team that won that last year for climate sciences, is given out for the largest climate simulation that is useful to human society. So we kind of know what we are doing, but unfortunately, there's no AI involved in this. And that's now the trouble. So what is the opportunity? Well, the opportunity is kind of interesting because we know the ground truth, this stuff is working, but it's slow, it's extremely expensive. It requires extremely large supercomputer. So the opportunity is to make the thing faster. So AI for science today, unfortunately, doesn't do that at all. AI for science, at least in that field, is not currently used to make simulations faster. It is used to completely replace simulations with things that could be very non-physical, and that is a problem. So we are not combining the two yet. So what I want to advocate for in the last 2 minutes is that we really should work with differentiable simulation. So we should have integrated AI models and not throw our equational knowledge away, because all the modern data-driven prediction models for weather and climate are not taking any of our physical biases into account. And well, if they do, then they get worse. This is the unfortunate thing. I spent 2 years trying to get the physical biases in, and priors, it always made it worse. So what I'm advocating is we should have a climate simulation. We should replace pieces of that climate simulation to help with the performance aspects of it, and then we can train this whole thing like an AI model. We do the typical thing, we compute a loss function. Then the only problem is that you have to backpropagate through your whole simulation all your gradients. So you now have a simulation part and you have a learnable part, which makes it significantly harder than what most people do today, where they just have a learnable part and you just learn free-form, data-driven everything. So we're basically missing that infrastructure to combine these two things into one and then achieve the most out of it. So in some sense, we need to backpropagate gradient through full complex simulations with million lines of codes. So we have a tool to do this, but again, I don't want to make this an advertisement here. So unfortunately, we don't do this. Just published a paper 2 weeks ago that doesn't do this at all, because it turns out all these data-driven methods are much better in practice. So now this is what we're going to argue. This is going to be my stance. I hope that somebody will hold against it and say, no, we need to do this better, but we'll see. So with that, I would like to, again, summarize. So I think we have not yet discovered an effective way to use AI models in many simulation domain sciences. So that's the provocative statement that Karthik was requesting. So everybody else will hopefully disagree. We should unify simulations and AI models. And here I worry most about the data type and the representation, but we can discuss that. What is working well? Short and medium-term predictions. In fact, ECMWF, one of the bigger the worldwide centers for predicting the weather at a global scale, is currently running simulations together with AI models, and the AI models get slightly higher scores, even though these AI models are totally non-physical, right? If you roll them out for a long time, all the water on the Earth will evaporate, and all the energy will live in 1,000 degrees. So that's very interesting. So what does not work well is it's rolling them out for a long time, as I mentioned. So we have long-term climate predictions that just don't really work. Even if the model is stable, I would claim we know nothing about the quality of the model in the future. So it's stable, we know it's not running out of bounds, but we don't know how good it actually is because we do not have equational background to explain it. So why can we trust these models is not 100% clear. And with that, I want to close my discussion and stop sharing and give Petros the microphone. Thank you.
Thank you, Torsten. That was a good start. Yeah, let's go full screen, yeah.
Discussing.
You want to move that Zoom bar?
What should I do? Hide it?
Yeah, hide it.
Okay, is that okay?
Yeah.
All right. So I'd follow up, and I would advocate actually for hybrid worlds, and I would, the same way that material science people are creating alloys, and when you make an alloy, the new thing is better than the sum of the parts. I would like to argue that AI and scientific computing can achieve this goal, and I'd like to give you some examples about that. So first of all, from scientific computing, simulation-based science, here's 2 of the simulations that I did with the team, of course. Cloud cavitation collapse. This is the Gordon Bell winner in 2013. We were finalists 2015. Both of them include 1 trillion points. One is grids and the other one is a particle-based method. Now, another thing I have been doing for quite some time, for the past 25 or so years, I have been working on machine learning. And in particular, I started doing that when I was a postdoc at Stanford. I took courses from David Rumelhart, who invented the backpropagation algorithm. And then I started to try to bring machine learning algorithms into fluid mechanics. And I was trying to show to people how actually machine learning can outperform classical methods like the proper orthogonal decomposition. The result of that is that it took about 3 years for that paper over there to be published back in 2002. And the paper that you see down here that you don't see now was even published before in 1999. Nobody want to publish that, so it appeared in the CTR briefs. Now, the other thing was at the time that computers were very slow. So even if you had machine learning and you could do all these things with neural nets, it was very difficult to do difficult or challenging problems. So what we did back then is we tried to automate experiments, and the experiment we automated was the optimization of combustors in gas turbines. So we used genetic algorithms and we enhanced them in order to be able to do to avoid noise and so on. And I'm very proud that there is patents that were produced by the algorithm itself, and now some of this turbo machinery is actually at work. So this was again 2002. Moving on, I thought that another place where AI could benefit is biology. So back in 2005, I talked to biologists at ETH Zurich, where I was, and then I realized that they were trying to infer the behavior of viruses by tracking viruses by hand. So what we did is we automated the video acquisition process, and then we used machine learning to do the classification. The colors that you see is automated classification of the trajectories that actually can help you to understand the behavior of the viruses. And we actually gave them ways to monitor cells. Now, I went back to fluids and biology in some sense. Back in 2013, we brought reinforcement learning to fluid mechanics. And this is one of the simulations that I'm very proud because it involves state-of-the-art simulations using wavelet-adapted grids, deforming bodies, and at the same time, control laws for the movement of these swimmers that have been derived by reinforcement learning. And I believe up to that time, it has been very difficult to get controlled motion of interacting swimmers. And now back to the old hobby of solving equations, but now with a lot of knowledge from machine learning. So we are used to solving equations of this kind, which is a differential equation. And what we do is we come up with numerical methods to solve it in a grid. So being inspired by the agents of reinforcement learning and considering the problem of discovering a numerical method as a problem of control, what if you have agents in there, you don't have grid points, and then the agents are talking to each other and they're discovering numerical methods. Now, the best thing from all these things was to actually put the numerical methods and the simulations together. And so what we are advocating is to use the numerical method to whichever capacity you can, and then to use closures that are coming from reinforcement learning. And here you see what reinforcement learning was able to outperform Smagorinsky models that in the case of homogeneous turbulence are kind of optimal. And not only that, we were also able to train in turbulent channel flow and to forecast in turbulent channel flow in Reynolds numbers that nobody has achieved before. This was work with Jane Bae. And also taking something that you have trained for a channel flow and applying it into a turbulent boundary layer, we got excellent closure models for this kind of things. Now, a lot of people are using reinforcement learning and they don't get it to work. I think in order to get reinforcement learning to work in fluid mechanics, you need domain knowledge. You need to be able to understand what are the states, what are the actions that you give to the system, and you should not expect that you plug in reinforcement learning and it's going to work. This was actually my lesson, which was not so bitter after all. And now let's talk about physics-informed AI. And of course, many of you are familiar with physics-informed neural nets. Probably very few of you are familiar with this other work. We call it optimizing a discrete loss. So if you want to solve a set of equations and do inverse problems with physics-informed neural nets, instead of plugging a neural net into the equations, take the discrete form of the equations and do it as an optimization. It's the same idea as pins, except that the ODIL is hundreds of thousands times faster, and because it is sparse compared to neural nets. So try for yourself. Here's something I did. There is a lot of advertisement that pins can discover the singularity of the Navier-Stokes equations. I think this is a very valid point of work. But then you can also take ODIL and apply it to the same problem using classical numerical methods. You get the answer much, much faster, and you actually get better residuals. And in fact, we are interacting with medical people to do inverse problems where we're using multimodal data, put them as a penalty term, the same way as pins have it, to put it in ODIL, and to try to do interesting problems in cancer modeling. Now, another thing we're working on and moving on and evolving together with how the field is evolving is to try to use genetic programming algorithms. And at AlphaEvolve, I spent a year at DeepMind where I had the chance to experience this machinery and to develop wavelets that are data-driven. You don't pre-specify the wavelets and compress your field. You say, I would like to compress my field, give me a wavelet. And then it's interesting to see the wavelets that you get from mathematics and the wavelets that you get from data. But I can tell you that for certain particular data, the ones that you adapt to the data are much, much faster. And then we are using this adaptivity in order to solve equations from these adaptive grids. Now, for the future, all my life, I had the experience of being taught by amazing people, and I had been the curiosity of exploring different fields. And now when you explore the different fields and you try to put things together, you do whatever knowledge you have, and in some way you are putting all these things together and you try to compile and to solve a complex problem. I believe that in the future we have the capability that we can give these simple elements in a certain way and then have people and agents working together and trying to do this composition on their way. I believe that the biggest challenge in this endeavor is the communication. How do you get agents to talk to other agents? How do you take agents to talk to humans? I believe that language is a very limited way of expression. I think it would be amazing if we could communicate by talking or having our brains map to each other and find the proper handshake, find our emotions, communicate with each other and find a handshake. Maybe you realize that when you have a person, a partner, or someone else with whom you communicate very well, you find out that things are much, much easier without even talking. And I think this could be the communication between agents and humans, or perhaps we can get rid of humans, is something perhaps to explore in the future. I'll stop here, and thank you.
Good remarks, but you forgot to introduce yourself, but I'll do that for you later. All right. So you want to go up? Alex, want to go up? All right. You can go up, Pedram.
Working. Okay, great. I'm Petram Hassanzadeh. I'm a faculty at U Chicago, and my background is in fluid dynamics and applied math, and now I mainly work on AI for weather, climate, and turbulence. So I'm going to talk about a few things, those stuff in red, mainly in the context of AI, weather, climate models, but I think a lot of these apply more broadly to many problems in using AI for multi-scale dynamical systems. So as you might already know, we are going through a second revolution in weather forecasting, and this is driven by AI. So here the idea is rather than solving PDEs on supercomputers, you train a big neural network that takes the current 3D state of the atmosphere and predict it 6 hours or 12 hours later, and you put it back and you basically march in time like an initial value solver. And this idea has been around since 2017-18, and most people thought it would not work because we only have like 40 years of high quality data for the training. But it turned out that you can actually do this. So there's this paper from NVIDIA that introduced a model called ForecastNet. My group and a number of other groups contributed to this. And we showed that when you have a big enough neural network trained on these 40 years of high quality data called era 5, you can actually get close to the accuracy of the best physics-based weather models, while this model is 100,000 times faster and tens of thousands times more energy efficient. And now there are a lot of tech companies that have developed models that are even better. So these models robustly outperform their physics-based models. You might hear about them in the news all the time. And these are not things in the news or just in the news or some academic papers. The operational weather forecasting centers like NOAA or ECMWF, the European Center, all agree that the AI models are better. This is a plot from ECMWF comparing basically the pattern correlation for one of the global variables between the physics-based model, they're in red, and the blue one, this the AI model they have. You see that you gain half a day in the forecaster skill lead time, while the AI model is 100,000 times faster. And now there's a lot of excitement about these models. There are many reasons that these models can be very attractive. Billions of dollars are now poured into this by many investors for various reasons. For like low middle income countries, these models can be a game changer. Also to do probabilistic weather forecasts, do UQ and things like that, these models are very attractive. There's also now a lot of interest in pushing this into subseasonal, seasonal time scale, and even do kind of climate prediction with these, and we can talk about how that might be possible. But in the past couple of years, now a number of papers have emerged that also point out some major problems with these models. So one of them is showing that these models actually don't have butterfly effect. So here what I'm showing you, the y-axis is the variance of an ensemble prediction. So if you initialize these models and perturb the initial condition at the level of current observational error, you see that the physics-based model, which is blue, and the AI model that is red, basically they have the same growth invariance, which is fine. But that's not the butterfly. Butterfly is when that perturbation, the amplitude goes to 0. Now, if you scale down the perturbation by a factor of 1,000, then you see that the growth in the variance in the physics-based model is exponential. This is the butterfly, while the AI model doesn't do that. So this is like evidence that these models do not reproduce the butterfly effect. There are now more papers showing that whether you use a diffusion model or transformer, whatever kind of AI model you pick, none of them can produce the butterfly effect. Another question about these models is, can they predict events that are stronger and rarer than what they had seen before? Can they actually extrapolate from the weaker events they have seen? And many people thought these models can do this because they can learn from weaker events. So we did some work and we took one of those models, ForecastNet, and we trained it with all the data. We also trained a version when we removed any sample that had a category 3, 4, 5 tropical cyclone, we removed those samples from the training. So a category 5 storm for this model is what we call a gray swan, an event that is physically possible, but this model has not seen anything like that. And it turned out the models cannot forecast it. So we see that this model can forecast a category 5 storm fairly well, while these models can never get into that kind of low pressure level. So they cannot extrapolate to more extreme events. One thing that we found as surprising, and we call that translocation, is that it turned out that these models, as long as they have seen events in one region, they can predict them everywhere, which is kind of interesting. So they don't overfit on a specific topography and latitude, longitude, which is not something that people design this, but the models have that. The other issue is that these models, of course, lack causality, and it shows up in the problem that they might get you the right answer, but for the wrong reason. So now something that many people are doing is to turn these models into boundary value solvers. So you can add basically another input variable here that might have the ocean temperature, CO2, other things. So you are going to learn the evolution of the state conditioned on this boundary value that you have. And we know that the causal relationship here is that you increase CO2, it would warm the ocean, that would warm the atmosphere. And the way that these models have been tested is the same way that we test the physics-based models, which is you prescribe the ocean, and then you see whether these models can capture the observed trends. And what I'm showing you here on the y-axis, this is the trend, Kelvin per decade in different latitude bands. These circles, these are the best physics-based models we have, and you see that usually they don't agree with the observed trend, and these are because of the problems they have with parameterizations. There is a square here, and that's one of the fully data-driven models. And you see that that model actually does a great job capturing the trend. It even does better than neural GCM, which is a hybrid model. It has an AI parameterization inside the PDE solver. It's a model from Google. And the fully data-driven model does even better than this hybrid model. But it turned out at the end that the model is not really learning things in the way that I described, that CO2 warms the ocean, warms the atmosphere. It actually learns everything from the time that providing the time series of the CO2. So it goes around, it basically circumvents all the physics. It just learns from the time and gets the trend out of that. It's like our example of that famous example of the AI doing diagnosis by looking at some text on an X-ray rather than really looking at the X-ray. Another problem we have on these models is that they cannot capture slow-fast dynamics, which may not be very surprising. The loss function is basically supervised learning focused on fast dynamics of 6 to 12 hours. But then at the end of the day, the atmosphere has many low-frequency variabilities at the time scales of months and years, and the models cannot capture those. Another problem we have found with these models is that they cannot get out of distribution force response. So we know that when the ocean warms, the land is actually going to warm faster. That's basic physics. The physics-based models actually reproduce that fairly well. We don't know whether these amplitudes and patterns are correct when you warm the ocean by 4 degrees, but at least the physics-based model gets the basic physics correctly. On the other hand, this is one of the best AI models, the one that, again, with many metrics that we care about, does very well, better than any of these physics-based models. Once you warm the ocean, it actually cools the land, which is like a major problem. So to basically summarize some of these, so these AI weather climate models, again, with many metrics that we are used to apply to physics-based models, they actually do very well, better than the physics-based models, but they basically lack butterfly. I didn't talk about interpretability, but basically we have no idea what these models do. they don't extrapolate, they lack causality, and cannot capture fast slow dynamics. In terms of what we need, I think, well, of course, we need better metrics and benchmarks, especially those that they can identify when the models are getting the right answer for the wrong reason, which might be very hard, like for extreme events. We even don't have enough samples. For grace ones, we even don't have any sample to test these models for them. We need a better understanding of what data might be missing from what physics might be missing from the data. Karthik has a nice paper talking about some of these that with coarse graining that often is applied for the training data, you are going to lose some information. And I think missing that, the physics that's in that information actually can cause problems with capturing some of these. And of course, we are all interested in physics-informed learning, but the question is what physics to add and how to add it and how to add the physics without really destroying what we were gaining from learning from data. And at least for weather forecast models, I think there have been a lot of efforts in trying to build some physics into the models, and they always ended up degrading the accuracy, at least for weather forecasting. Now, in terms of possible directions, of course, one is I think we might need fundamentally different learning algorithms, at least for weather climate. So far, everything has been about taking a standard approaches, adding a little bit of physics, a little bit of numerical analysis, and again, getting these models that can do very well in many metrics, but again, they have these issues. But I think we need to move away from this supervised learning, focus on fast dynamics, and even I'm not sure whether the current SSL approaches necessarily can do better. The other approach would be to try to accept that we have these imperfect physics-based models, imperfect AI models, and we are going to integrate them. And here I'm not necessarily talking about the approach of having AI-based parameterizations inside the PDE solver, but just really to have these two kind of models and try to integrate them using some mathematical or statistical algorithms. We have one example in that we basically use an AI forecast model to guide a physics-based model where to sample to get more extreme events, basically use a rare event sampling algorithm to connect the two. And you show that you can really accelerate the sampling of the most extreme events, even gray swans, using AI, while all the statistics, all the samples still come from a physics-based model. So I think like that's the kind of approach we can think about. So with that, I stop here. Looking forward to the discussion.
Can we hear me? All right. That never works in the first try. Okay. What's up? The same? Oh, I didn't know that's. Yeah. I thought it was just shared. Introduce yourself. Allow. On Zoom, I should, yes. How to. Okay. Oh, I thought we were just doing everything for
the entire screen. One of the two.
Okay, I'll get that moment. Oh. This one. Turn this window. Yeah, but you need. Yeah, I'm not sure. Okay. Oh, I think we can get it.
Yeah, I think it's showing up.
Oh, okay. We're just go over there. No, I think we got it. Can't see shit up there. Oh, okay, we're doing both of them. Fine. Let's get over here. Okay. Cool. I wanted to use half of my intro time to just screw around. Okay, and that moves. Wonderful. All right, Alexander Lavin, founder, CEO of Pasteur Labs. I also have a 501c3 nonprofit sister organization called the Institute for Simulation Intelligence. The slides up here are part of a presentation that I crossed out on the bottom. I thought that would be, I don't know, intriguing that the same things here at this very, well, mostly academic forum about AI and physics and the things in between or not in between. Same materials, same bits that I shared at a very industrial engineering symposium that I was invited to give a spotlight on applied AI just a few weeks ago. Pasteur Labs, this is what we do. These in silico playgrounds for human machine teams, the operative, I guess, statement there. And to be, well, I guess a good panelist that can like spur some controversy and discussion. And we were asked to share examples of real use cases. Oh, cool. It's not showing up on mine, but it's up there. So this is one of those in silico playgrounds on our platform, the SI or Simulation Intelligence platform. And I'd be more than happy to get into the demos for these different workflows and how they live in containers and literally multiple, what we call multi-physics modules that have lightweight surrogates. You just need 1 to 8 GPUs to train in hours, and they run inference. I have models running on my iPad in my bag. And here, these are running, the top one in a, what we call a tesseract. It's a fancy container. It's fancy because it's end-to-end differentiable. So it has Jacobians, Hessians, endpoints for backward or forwards and backwards. That's the hard part that all the open source, I think you know I'm talking about, differentiable programming frameworks don't really test and validate at scale. And what was going on in that demo there was a test rig of a supercritical CO2 heat exchanger. So not like bootstrapping with the ground truth physics equations as best we know them. And then on the test rig, pumping in live sensor streams into the machine learned surrogates. There was one at the top, we call it the what if surrogate module. That's what if questions, counterfactual reasoning within the appropriate solution space. And that's one of the, well, let's say examples or ways to illustrate how I started this company. The team on 4 continents, just over 50 people now, joined this company to close simulation to reality deltas. And what is up here, right, so we had a fantastic introduction to Nobel Turing yesterday. And this is in our incorporation documents as a public benefit company. To be clear, we are very, very for-profit, venture-backed. I'm one of our main investors. Public benefit corporation with that mission statement is legally binding, basically holding me as CEO accountable. If there's a board meeting, like my board is here in Chicago, I'm from Chicago, it's fun being home. I live in New York. I have a quarterly board meeting tonight. If we're going over budgets and revenue streams and we see that 72% of revenues are coming from selling Earth observation data to hedge funds, the board is required to fire me on the spot. That statement for Nobel Turing is intentionally broad and vague, but holds me accountable nonetheless. This is a phrase that really helps my own mental model for the multiple flavors and dimensions and complexities of models, physics-based, data-driven, semi-mechanistic, causal. And this helps, well, convey how we view integrating artificial intelligence. I don't really like that word so much. It's really physics-informed, physics-infused machine learning, and approach real industrial R&D problems. So this high-dimensional space of simulations, one particular simulation, numerical, like some colleagues up here have shown, or something that you build in ANSYS fluid dynamics software, for example, is a vector to this point in high dimensional simulation space. And it's a vector because the origin is specified, it's grounded in the physics governing equations. A surrogate model predicts points in the simulation space by mimicking that simulation vector. It is a function that outputs independent point predictions each time you run inference. There are details and nuance to that we can get into around that point in the simulation space, which is terribly useful, also terribly misleading in ways to just as humans think that like here we are with a technology, draw a straight line up into the right. That's where our capabilities will be next week. And what we're really interested in is this amorphous blob, this blue blob in the high dimensional space that includes that physics scenario that you defined a priori and the variations around it. The surface represents much more diversity, known and unknown, that took weeks to start to, well, parameterize and point that vector to for any given research engineer or computational scientist in some specific domain. And a program or simulator outputs many of these simulations to represent continuous sets of that solution space, or like a vector space here in more purple, and the diagram gets very purple and confusing. And this is how we view our technology. The platform, SI platform, is end-to-end differentiable. And we've built over the past half decade interfaces and modules, templates, validations of end-to-end solutions that you can plug and play with open source solvers and some awful Fortran code that someone in your lab 2 decades ago had there, but it works and just don't touch it, but it doesn't play nice with anything. Now you throw it in a tesseract, one of those fancy containers on our platform, and it passes those gradients forward and backward, and it plugs and play with ANSYS tools, OpenFOAM, anything that you're building in pick a machine learning or agentic AI framework. And because I wasted so much time. Right, so controversial things for panel discussion. I have a lot of thoughts at low-level maths and in higher level, like corporate development speak about the extreme scale of foundation models, just like already in this kitchen sink conundrum, whereas there's more and more detail in both model complexity and data. And as that's thrown into a simulation, there's no guarantee that it will get us closer to understanding of reality itself. That seems like a question we all care about, but is lost on industry and a lot of the other startups out there. And with all this complexity, you end up getting like an insanely chaotic latent space. And at least in computational engineering, broadly in industrial R&D, being able to navigate continuous spaces and iterate over designs and tests and design of experiments, inverse design, integration into system of systems for multiphysics. Like you need to go one step after another, and it's all these like back and forth, and it's you can use these models to spit out predictions of designs, and you can produce some like GIF animation, but that just like goes through them seamlessly and it looks cool, but that doesn't mean the latent representation is doing anything continuous there. Multiphysics modules, would love to talk about this more. I'm going to skip over this because it's really fun. Skipping this to, let's get to, I don't just come up here on stage and talk, let's say, poorly, or feeling another word, about other models and approaches. The way I describe our publication record internally with the team, this is a cool new paper we just put out last week. This is Tesseract's open source product. We have a nuclear fusion team, Nobel Turing Technologies, Advanced Society, et cetera, et cetera. That's a big money loser, but that's why I started this company, is to just, the timing was right, the technologies were there, the people on this mission. Open source, go try it out for yourself. You get a lot of fun advances like these. MLflow built in, end-to-end demos on tons of diverse domains. It's published in Journal of Open Source Software. Also forum where my staff will help you get onboarded and solve issues. And that's all. Thank you. Thank you very much.
Rafa, do you want to come up on stage as well? Yeah. All right. We should.
Of the internet.
Oh, okay. Can we get a mic for Rafa as well, please? All right. But I think, yeah, thank you for the opening remarks. I think we should get started. So I think, yeah, Torsten, I think your distinction of what is uncompressible versus what is compressible and how AI can, have a role was, I think, pretty eloquent. So, I want to start there, right? So clearly, the answer to, whether we should put in inductive biases is not binary, right? There are scenarios where it helps, and there are scenarios where it may help, and there are scenarios where it does not help, right? So given the very broad audience, and from your own experience, is it possible to come up with a very short description of when to use inductive biases, when to not? Again, it depends heavily on the context, but I'm trying to see if there is any contextual simplifications you can offer in that regard.
Yeah, that's a great question, and my answer is going to be very disappointing. So
that's fine.
So all I've seen in practice that works is using only the weakest inductive biases, which is very disappointing. So, for example, using GNNs as an inductive bias. I mean, a model structure is an inductive bias, right? So if I'm using a transformer, if I'm using an MLP or a GNN, that's an inductive bias. So we choose model structures for scientific problems, but as Rafa has pointed out, I like that argument, is that even if you look across different models, the internal representations become similar. So these inductive biases, they may not be too useful at the end. And what we've seen for weather and climate modeling, for example, I mean, we've seen ForecastNet, we've seen GraphCast, we've seen AIFS, which a colleague mentioned, and that was I mean, there's a graph neural networks as well. And we've seen completely different approaches like transformers. All of them are essentially equally good at the end of the day.
Excellent.
So that is extremely disappointing. Can you give me, and I will not argue with you, so can you give me an example where you have a strong inductive bias together with a model that is actually successful?
Okay, I can, but Petros raised his hand, and I want Pedram to answer as well. Yeah, Petros, go ahead.
I actually showed it. I think the domain knowledge is something that it would be a waste to throw it away. You can see it as data that you're throwing away.
I think so too, yeah.
And so, for example, in the case of closures for LES or for runs, as we do now, I think if you are careful about what is the inputs and what are the states and what are the actions of your reinforcement learning, it could be the neural nets, then you can gain a lot of speed up, a lot of things. And a Bayesian way to see this is actually you have the likelihood, which is your model and the data, and you have a prior. And the better your prior is, the faster this thing is going to converge. So having domain knowledge for me is writing down an equation. It's a prior. And then that helps you accelerate your discovery. Of course, there can be other problems where you say, my problem is a massive combinatorial space. Doesn't matter what's going to happen. The inductive bias is going to disappear. I agree. But it's all a matter of how many resources you have, when do you want the answer, and sometimes you want some guarantees that you will get an answer. And I think the inductive bias gives you some guarantees.
Yeah, I think it's a good point. I mean, I just want to add a little bit because you did ask me a question, right? So it also depends on how much data you have, right? Let's not forget that. I think Petros mentioned resources. I would put data in that. If you have infinite amount of data, yeah, of course, we don't want inductive biases. Maybe it's inefficient way of doing it, but in many cases, we don't have that. But Pedram, I want to, again, in response to this, push on some of the things you showed, right? Depending on the question you were asking, purely data-driven models were doing phenomenally well. But in the same problem, same data, you change the question, and they were doing very poorly, right? So maybe you want to add something to the discussion on those ends?
Sure. I mean, actually, like about the first point, like in some simulations of turbulent flows, like simple geometries, when you don't have enough data, adding symmetries or equivariance, things like that can help a lot.
Yeah.
But then when you have a lot of data, you actually don't need those. Now, for weather climate, I think exactly the question is what your current model is missing. In the case of like forcing the system, I think there you might see an advantage of like having energy conservation. People haven't done this yet, but my guess is that there, if you had energy conservation, you might see a better forecasted scale, but you might see a more reasonable response to a forcing.
Correct.
The problem is exactly on the energy conservation. I've seen so many approaches that failed. Like with the ECMWF, for example, they tried it, it failed. The only problem is that and there's one problem in our approach here. The major problem is these failed approaches, nobody writes papers about.
Sure.
So we can always point to success, but there we cannot say, oh, this is actually a thing that's at least hard. Failure doesn't mean that it's guaranteed to not work right, but it means that smart people have failed. And that's disappointing.
Yeah. But I think it brings to the fore a bigger point, which is there are many situations where just putting in inductive bias, even if it looks appealing, does not help, right?
Yes.
So I think we need to have that broad perspective.
But how do we quickly determine whether it helps or not? Because what I want also from you, Petros, is a recipe, right? So let's just say, oh, I have a result here that has worked, but how do we actually teach this?
I can
Go
give
ahead.
you my opinion.
Yeah.
We say a lot of data. I think you need to normalize what a lot of data is. What is the degrees of freedom you have?
Sure. Yeah.
If the degrees of freedom you have are very high, then you need immense amounts of data. So whether you have a
That's
lot
the
of
triple
data
statement,
or
yeah.
not, for me, it's also what is the governing degrees of freedom of your problem. And for figuring out what are the governing degrees of freedom of your problem, maybe one day we will automate this. Probably we will automate this. But at the moment, I think domain knowledge constrains the degrees of freedom of how to look at problems. My opinion.
Yeah, very good. So this is a good starting point. We'll get back to this point. At this point, I want to stop the people who talking about flows and turbulence and get to, Rafa, what is your perspective given what you've seen in your field regarding inductive biases constraints?
I've been sort of the inductive guy as by department, and that's what got me tenure. Like that was like my tenure package. And now I'm like, I don't know. It's how long do they last? I think like when they work, they kind of don't last for too long. So like, CNNs have some, compared with what people were doing back in the day, ImageNet, like it was the bitter lesson comes from machine vision with CNNs.
Right.
But even CNNs kind of recapitulate vision a little bit in the structure of vision, but vision transformers are now better than CNNs. So even whatever amount of inductive bias lived in CNNs, it's kind of been distilled away, which is being boiled away by making bigger models. So I think there is sort of a time factor in the question you're asking. I was sort of, it was, we saw it with equivariance, right? We had invariant models and they weren't very good, and people sat down and, they wrote down the spherical harmonics. It's like, yeah, this is more expressive. This has more information. And they were better and more data efficient, but way slower to train. And then the next turn of the knob was, you know what, let's make models that can express equivariance among other forms of non-invariance. Now, there are models that are variant, and if you rotate your frame of reference, everything changes, and then you harness them to just respect equivariance at the end. And it turns out those are just as good. AlphaFold 3 is not equivariant anymore. AlphaFold 2 was equivariant, AlphaFold 3 is not. So I don't know if, I just don't know. Are we the last stand of inductive bias in this, as scientists and physics-driven people, are we sort of the last stand for inductive bias? Or will we really sort of stay? I don't know. I just don't know. Equivariance is the thing that went away over the last 3-4 years in
That's
my
very
field.
good. That's a very sharp observation. And just to baseline it, right? So going from AlphaFold 2 to AlphaFold 3, did they use more data, or it was the same amount of data?
They used the hundreds of millions of predicted structures with AlphaFold 2.
See.
So, but this is insane, right? Like, so you get an older model, you create lots of data with it, and from that, you're able to distill a model that is better out of distribution, having ingested a lot of sort of in-distribution data from a prior generation of the model.
Yeah.
And so I hope you know the answer of this when you ask the question. But it makes it even worse because it means that inductive bias is a crutch that we will get rid of and distill away. Gabor has a question, and I think we should let him fire away.
Yeah, actually, maybe you can have a quick comment.
Yeah.
So I'm going to do my question, audience question, my question.
Okay.
So we'll switch. But a quick comment from you.
Yeah.
So
Not
start
the
from
last
the
stand
beginning.
for inductive biases. Everywhere, up and down engineering life cycles, I see in industry, aerospace, spacecraft systems, energy production, automotive safety, where chemical processing, where you have a cascade of effects and having what we call dynamic surrogacy, where the first, let's say, compressor or pump or valve has inductive biases, like overwhelming inductive bias for what sort of surrogate model that you're going to produce, and you don't for the next one, especially when it's a closed loop system. When that comes back around, you're able to, in a fundamental way, understand the incompatibility of the new dynamics coming into that upstream compressor system dynamics because you have inductive biases. If you put inductive biases in the next one down, you don't have the second order effects of propagation in such the system. So there are so many small scale examples like the AlphaFold 2 to number 3 that industry, from my perspective, is waking up to and finding, oh, our domain expertise, our engineering intuition, really useful to shove into machine learning models.
Yes, very good. Thank you. So yeah, so there's a multiple axis here, like the amount of time you have, data you have, questions you're asking. So it's a multidimensional space with no single answer. But so, all right, let's take a question from the audience and then come back to prepared questions.
There's one.
Jerry.
Sorry. Yeah.
Failure of butterfly effect is really interesting, not seen before. So is that because the diffusion models doesn't respect unidirectionality of time? And do you think if you use the failure of butterfly effect as a symptom, what's the other?
Giri doesn't even need a mic, but
Yeah. What's the other, you can speculate what's a model fails in other more critical things.
So the results I showed are actually from a deterministic model that uses a transformer. But then the next paper showed that whether it's a diffusion model or it's a deterministic GNN, deterministic transformer, they all have the same behavior. So it's not necessarily a diffusion problem. And it's still unclear where this problem comes from. It could be really a problem of having like a loss function that is focused on 6 hours. So the model doesn't see a growth of an error in 6 hours, right? So it could be a problem related to that, but still, this is something people haven't figured out. Now, in terms of what problems this might be causing, I mean, these models do very good weather forecast, better than the physics-based one, right? But also the weather community knows for a long time that butterfly is really not that relevant for the skill of the weather forecast, the way we measure it. But again, down the line, there might be things that these models are missing. Clearly there's a missing piece of physics there, and that might have other effects.
correct. And just to like zoom in on that, right? So purposely they remove high frequencies from the data and then give it to the model. So of course the model's not going to get, or maybe even if it has those, it may not get, but I think, yeah, you want to.
I just wanted to follow up on that because I was very impressed. Is that I didn't quite get, is that a feature or a bug? Is having the butterfly effect that a signature that things are working very well, or a signal that sort of in the way we're integrating over time and trotterizing time, we create sort of this problematic condition?
That's a great question. I think this paper freaked out people a lot because people interpret this that these models are not chaotic, that's not true. But I actually think the reason that these models are so accurate, well, more accurate than the physics, is actually that they don't have butterfly. They don't have this growth of these smaller scale things that down the line you actually don't need them, right? Because we care about what is the weather over Chicago, right? We are not thinking about where this wave is going in the atmosphere, right? So actually, we have a paper that we try to argue that lack of butterfly is actually a good thing.
Okay, short question to you.
It depends on the time frame, actually. That is the important thing. So what's your horizon? Because butterfly really matters in a very long horizon, but doesn't matter in a short horizon. And right now, there's no model that predicts very well for more than 2 weeks. Right. So that's I agree with you, but you have to be careful. If you go to climate and seasonal, then it gets very different from what we have, where we have the skill today. Right.
Yeah, I think that the problem could be also from other things, like from really communicating with the land and ocean and other things. But I agree.
All that.
I mean, it could show up, maybe back to your point about like the quality of the ensembles we generate, right? But again, like we still don't know, like we know that the probabilistic forecasts are not calibrated from these models, even GenCast, which is maybe the best diffusion model out there. But anyway, yeah, it could be like showing up at some point when you hope to have a good bit of ensemble.
But there may be also an issue on the other end of the spectrum, right? If I am a wind farm operator and I want details, yeah, that you don't have that, right? But in any case, I mean, enough on weather, but you know, it's clearly a huge success of machine learning, right? So we leave it there. Any other quick questions? Yeah, go ahead.
My name is Ismail Al-Khoury. I'm from Lionel and the University of Michigan. In my research in solving inverse problems for computational imaging, I've seen both cases where the architecture design is essential, and in cases where in diffusion models, the architecture actual design does not really is converging to the same as in your point. So my question is, like, for the case when we have weak inductive bias, isn't that an indicator that the architecture that we used is not good enough, or it's a bad design, or should we do a better job, and should that be the focus instead of going after like more compute, more GPUs? Shouldn't that focus on the architecture and improve that inductive bias? Thank you.
Who wants to take it? Go ahead.
I love that question. I think the answer is yes, but can you come up with a better architecture? I mean, as we just heard, attention is eating everything, right? Attention is an extremely generic architecture, but it gobbles up everything if you give it enough data, like you mentioned. And now the real art is in coming up with a smaller representation where these inductive biases come in, which is what you mentioned, right? But now, what is an inductive bias? It's something that a human has observed. That we need to keep this in mind. What we call inductive biases, we assume that there are fundamental laws. But any model that we use to model reality is an approximation of reality. So we're losing high frequency things and left, right, up, and down, right? And so now there is a question between fidelity of the model and the actual prediction and the butterfly things and all of that. So this is where it gets complicated. And that's exactly the question I was posing to Petros. It would be great if we would have a scientific approach to take an inductive bias and encode it into a model, which right now we don't. We have all these ideas like pins and up and down.
There is an inductive bias in that inductive bias.
Yeah.
So very quick comments.
Yeah,
Petros,
we just like roll
second
back
order.
the AI research literature like a decade, probably even less. We get it, well, I don't know, before GANs, where there's computational neuroscience is the source of how do we programmatically include inductive biases. And that's where we have like information theoretic approaches to exploration exploitation over an image space or just any generic space that is supposed to be a map of reality, to your point. So you said attention is eating up everything. It's like, right, since there's been computational sensory motor, I don't know, let's just say soft computers in our brains, and attention is how we like programmatically understand and act in our world. And there's, well, from my view, zero coordination connection of like attentional mechanisms and research down that pipeline relative to attention in latest architectures. So assuming that like attention is just like how it was defined yesterday or a few weeks ago by the latest AlphaFold or something, is a slippery slope. Let's not forget kind of like the foundations of, well, inductive biases and why we have biases in the first place.
Petros, quick answer.
So besides an episodic proof that inductive bias is useful, I think another way one can try to answer this is through the Bayesian way, which is the model evidence, where you are trying to integrate out all your degrees of freedom, and then there is a comparison between models. Now, the problem with that is that for machine learning models to do uncertainty quantification in the Bayesian way for machine learning models is almost impossible. So that maybe one day we will have the computers to do Bayesian inference in gazillions of weights, and then we will have the answer to your question in a very Bayesian proper way. So that would be one way to put it. If you have an inductive bias where you limit the number of parameters, then we can answer this question already.
Okay, all right. I want to switch gears now. We did not talk about this yesterday, but this is a surprise question for the audience, for you, sorry. So we talk about inductive biases, we talk about human AI, we talk about physics AI, but let's talk about how we can do AI interactions better, right? Like we have, how can societies of AI agents, for instance, come together? I mean, how can we improve that aspect of interaction? I don't know, maybe Rafa, you've done something.
I mean, in a sense, I think the position we've taken is that we're going to train one model. So I think the emergence, and this is what happened to large language models, right? Like I think if you had set out to write a transformer for coding in 2009, you wouldn't have arrived to where we are if you try to make agents for coding. So it turns out it was LLMs that learned English and French and and everything out there and code turned out to be very good at coding. So I think there is some hints out there that the emergent behavior comes from scaling up across tasks as broadly as you can. So I don't think this is about making an agent that, a specialized agent that, selects the menu for next week, and a specialized agent to select the recipe, and a specialized agent to like dispel the trash, right? Like now we've seen, and I think at the end of the day, if you only have one instantiation of a model, one set of weights that you instantiate multiple times for them to sort of self-play in some, ecosystem. Thank you. In a sense, it's a trick for test time scaling. We've already shown inference time scaling is another way of getting scaling and better lessons. Like, it's not just the compute you use for train and the data you use for training. You can also apply this trick to inference. So by instantiating multiple agents that talk to one another, you're kind of using more inference compute, which gets you back to the same narrative. So I don't think there is sort of, emergent behaviors on this network of agents as much as the same scaling we've been seeing through and through.
Real quick, I'm sure there are updated versions of this, but the AI economist from the Salesforce research team, like 2019, it was all about, it's very different. It's tax policy in like different instantiations of economies, cities, societies, and the emergence and sometimes convergence to Nash equilibrium, as one would assume with inductive biases, and often not. Again, I'm sure there are updated versions with more, AI agents as we think of them today. But I'd be surprised if emergent phenomena from agent to agent interaction, especially like over time, extending compute at inference time, lacks any sort of surprises or emergence.
Good. All right. So, yeah, you go ahead.
So instead of asking when, I want to ask where you include physics in the model. So I can think of data augmentation using like maybe symmetries, changing the model structure itself, and like pin style PDE loss. For your applications, do you have any preferences for how you include physics?
Data.
More data.
Right. Oh, no, not more. But other people, I've been talking a lot.
I think we spent quite a bit of time on this, but
this is the augmentations, right? Like, people put this in the augmentations, and this is the evidence seems to suggest that you put it in the augmentations, And that's sort of the most scalable way. Second most is the loss, and the least is putting in the architecture, right? And you know, this happened to vision, it happened to language, and it happened to representation learning over structure, right? At the end of the day, you make a transformer over Cartesian coordinates, and you just show with different rotations of the same thing in case you want to learn that, and you're good to go. So I would say the sequence seems to be augmentations is the easiest thing to do and the most scalable, and if not the loss, and if not the architecture.
That's a principle, but it's also the inverse in power, right? Yeah. But yes, it's kayak.
Yeah, I think that's a. I actually wanted to give up my question because you took it to agents, but then he brought it back. So I like this. So I wonder if the imposition of equivariance, right, is you know, it's a hard constraint on symmetry, right? And if you look at the dynamics of these systems, right, you know, there are true measurements, so they're dissipative, there's thermal effects, and so the true system is not perfect symmetry, but approximate symmetry, right? Which when you give it enough equivariant data and then take it back, right, maybe you learn the approximate symmetry better, right? So is it just that we then bring back inductive bias through approximate symmetry learning instead of full symmetry learning?
Yeah, I mean, yes, this is the same reason. Like people need to rotate the cats to get machine vision models to recognize cats. So yes, I fully agree. It's just that it seems that being lazy and just putting it, you know, in the worst possible place is the best solution, which is, I think, the part that we're trying to sort of all to grapple with. So I agree. I think, you know, it's the same with, you know, how much energy conservation you need for weather forecasting. It's like you need 6 days worth of energy conservation each. And if you wanted to run in 365 days, you know, whatever, the oceans boil away, and that's problematic. But for 6 days, you can totally hand wave your energy conservation, which is a deeply dissatisfying outcome, I think, for many of us.
That's how it goes.
Yeah, I just wanted
Introduce yourself also, so
yeah,
people get the context.
Kyle Kramer from UW-Madison. I just wanted to make the observation that like we're kind of talking about inductive bias as like in a sort of like uniform way, like does it help, doesn't, in some, you know, universal thing. And I just say that, you know, like for molecules and things like that, you have sort of translation and rotation. It's like an incredibly small symmetry group. And so it doesn't take a lot of data to augment to learn that. I worked in problems in lattice quantum chromodynamics where the symmetry group is like 9-dimensional at every site on a lattice, and there's 1 billion lattice sites. So you know the symmetry group is 9 billion dimensional or whatever. So that, and we've tried in those situations, you know, with and without, you know, like a hardcore architectural level inductive bias, and it basically completely falls over if you don't build it in. And so you know, when you think about how much data, this kind of speaks to the question about the theory, which I would love to have this theory too, but you know, the amount of data augmentation you need grows very quickly with the kind of size of these things. And so there's and then the previous point, which was about, is the data actually have that symmetry or not, right? You know, like you know, you talked about dissipative effects and things like that. At the Large Hadron Collider, people talk about, you know, Lorentz symmetry, but the detector is sitting in a particular frame. It's got feet on the bottom, not on the top to hold it up. I mean, all the symmetries are broken in the actual detector. The underlying physics maybe has it, but so all of these, I feel like we need to differentiate all of these different things and pull them apart if we're going to make like progress on the topic.
Yeah, great comment.
Sorry, it's more of a comment.
Yeah,
sorry,
again,
but yeah.
I think the thing we want to underline is, yeah, it's a extremely high dimensional space, and what you think is an invariant may not help the problem, or it may help the problem. It depends on the situation of the question. All right, so Ricardo, let me take a question and then come back to you, because I'll come. All right, I'll go to you and then to Ricardo, but I want to inject one question here, which is very important, and I want to make sure we have time to cover it, and then we'll come back to you. So I want to talk about inductive bias of a different kind. What do we teach our students in this era of AI, especially with these incredibly powerful models? I have a point of view, which I'm not going to talk about, but I want to hear from all of you. We have 4 professors, 2 startup founders, et cetera, right? All of you deal with students, employees. Right. So Torsten, can we start with you? Yeah, you start. Oh God, no. That's
It's
a tough one.
Sorry? It's low risk for me. I'm not a professor. I have 0 students.
Yeah, but you hire people. You hire employees.
Also support PhDs through the nonprofit.
Yeah. Anyway, so let's maybe talk about graduate education.
Sure.
What do we teach students in grad school anymore?
What do we teach them? So what I keep doing, and this is problematic, I think, but we can talk about it, is that we teach students all these inductive biases that humans made up because it's compressible knowledge, right? So it's easy to come up with a small set of things that explains a whole lot of stuff, basically. Like this is what I call compression. Like, so you can, based on something that a human can understand, I can explain the environment. And so AI models don't need that. Right? So they may not actually need this form of compression. So they may be able to explain more complex environments that humans could explain without, and so then you feel kind of sad for the humans. Immediately, you're just like, oh, well, maybe that is more powerful than I am in predicting and in learning. So
Especially it is good at this compressible stuff.
Exactly. And then you get very frustrated. So that's my problem. And so I'm still teaching the students the old way. I'm saying, well, we need to learn, we need to understand what we humans can understand. However, you need to keep in mind that there may be more powerful ways that do not rely on that compression, because we must have the compression to understand. Humans cannot understand these.
Otherwise, we cannot ask questions even.
Exactly. And so that's where it gets problematic and frustrating in my view. But all I'm trying to do is to make these students aware that they understand the things or get the feeling they understand, and then they can assess the power of these models and use these models. But again, frustrating and problematic.
Yeah. Quick shot from everyone else. So what's your thought on what we should be teaching students?
In general, that's the area that worries me the most about accelerating advances of AI, accelerating itself, turtles all the way down. The types of problems and algorithms in multi-physics perspectives that I have, my team has, and the students, whether it's PhDs or postdocs with internships or through my nonprofits that we support with grants, we are very interested in how you inquire and poke and ask questions about like the map, how, like, what is the delta from that with respect to reality? And the given is that the equations are wrong. All models are wrong, some are useful. The equations are fundamental equations of physics. Pick one, it's wrong. We can improve it and understand like where it's wrong, maybe improve it, sorry, with data-driven models and models that allow humans to become expert in asking the questions about the difference between the map and the reality or the territory.
Teach them to ask the questions about gaps. Okay, all right.
One of the things that I find exciting about AI is that you get people from different disciplines to acquire a common language and talk about AI. I think intelligence is something that fascinates humans very much. So on the basis of teaching AI, you can get people from different disciplines and different interests to come together. Now, when you bring these people together, one of the things you can try to teach them is to teach them philosophy. And I'm very sincere about that in the sense of how do you think about problems? What are the values that you have when you're approaching a problem? So teaching philosophy, which is a human product, and also to teach them to look at nature. I introduced a course last year at Harvard called AI, Computing and Thinking. And I can tell you which one was the lecture that the students liked the most. The students contains lawyers, philosophers, engineers, and all. They like the concept of stigmergy. Stigmergy is what insects do, and when they are building a nest, they're putting down some information. The next insect comes and adds to this information. So they found this fascinating, and then we started talking about how humans communicate. But so I think you teach them some very first principles, and I think the other thing we need to have is to have trust in the new generations. I think no matter how much we try, we cannot screw them up. and I think you just observe as to what happens. But I think teaching all things like values, principles, looking at nature, thinking in terms of the truth are important.
Yeah, thank you. I should have guessed this because you have a 2,700-year bias of those ideas.
Probably you have more, but
yeah, I have more. All right, go ahead.
Yeah, so I think like there are different aspects of the teaching question, but like one is I think students in all domains now need to be able to be critical of like when they pick up a paper that uses AI in their field, what questions to ask and what are the things that they need to be looking for. So I teach a course in like for geosciences students, and that's what I try to do. I think more difficult question is if you are teaching students applied math and numerical analysis, to what degree incorporate AI? And I think no AI at all and all AI, neither one is a good approach. So how to find balance, and it might depend on the student and what they want to. I think like that's a much more difficult question.
Okay. Yeah.
I think social media and TikTok show that you can totally ruin a generation. So we'll see about that. We might be the first time in history where we've managed to screw up the younger people. You say graduate education, and I had a sigh of relief. I think graduate students are definitely going to be fine. I think it's about being critical, discovery, some mentor discovery. I think they're peers at this point almost, right? So I think that, I'm sure there's graduate students in the audience who can make judgment calls and decide, I'm going to use it in this way. I think they're participants in the conversation, and I think they're empowered, and they will explore, and they will be the ones that find out how much inductive bias we need to inject in which form. So I think for grad students, it's, they're empowered, they're equipped. I'm deeply worried about undergrad education.
Okay, that's why I did not want to talk about it.
Thank you. So I'm going to slip it and then not mention it again. But I would say, I think we just need to get them sort of, get them excited for this to be. And I think the computer science folks are getting the sense that AI for science is the next. I mean, you're seeing, Demis Hassabis got a Nobel Prize, right? So it's a pretty easy statement to make, that the next exciting frontier for AI that has no downsides as opposed to many other things is AI for science. So I think it's all opportunity, I think, around graduate education and sort of AI for science.
Excellent. All right. There was a question there.
Hello, this is Noah Paulson from Argonne. So we've been hearing about how, we can try to put inductive bias in models through equations or loss functions or symmetries in the data. But what about the data itself? What opportunities are there for leveraging multimodal data, multi-fidelity data, different types of observations to improve the physical realisticness of our models and the results of those models?
Okay. Real quick, in a lot of industrial R&D applications that we see, there are the nominal scenarios, and there's the more frequent in reality non-nominal. So outside like the operational envelope of some pick an aircraft or a propulsion system for like a maritime vehicle. And it is far too expensive to have representative data sets about the nominal scenarios. Anyone want to ask questions about what's outside that envelope? So being able to inquire about what a model knows and like where and how it doesn't know what it's predicting, projected to this other dimensional space, not the latent space of the model. That is like for the downstream performance criteria. I know this does not matter for or map to, let's say, a lot of like the weather and climate experts here, but there are ways to leverage data that are not necessarily doing more and scaling in order to better understand that space. It's being intelligent about like this reassess before you run. So way upstream intelligence sampling of uncertainty in a performance space, not necessarily in like a latent space of a given model.
Okay. All right, Ricardo. Okay, so we have a quick question here and then,
Hello. Yeah, I have a question for Rafa. My understanding so far is that your position is against inductive biases that we instill into models, let them discover their own findings, see the world from their own viewpoint. And but at the same time, Lila's breadth is depth approach is sort of built on this expectation that if we follow the footsteps of the pre-training era, the chinchilla scaling laws, we might find a second wave of emergent behaviors where, the models can discover novel associations across different scientific domains. It worked once we trained LLMs on all of the internet, and they were able to translate from English to German. But the very definition of an emergent behavior is that it is unexpected. So we don't have a scaling law. We don't know when we will arrive there. Isn't that expectation an inductive bias in and of itself? That
I mean, I would say I believe deeply in physics-based sort of mathematical, I like compression. I believe deeply in it, right? That's what I'm less than others, but I've been trained on. So it's just that, the evidence in other places seems to be that we need to be mindful about sort of the amount of sort of, fulfillment and local performance we get versus this steamroller of scaling. So it's not that I believe in scaling is that the evidence in sort of the fields when it comes in and touches a field with its magic wand, that's the field that sort of runs out. And weather forecasting turns out to be, and then it didn't need 1,000 years of training data, right? It needed 40 years of training data. So it's not so much about having lots of infinite amounts of data. It's like in the fields where they were able to sort of lock into this paradigm, things moved in a way that was surprising. So that's what sort of the message that I've kind of convinced myself of over the last 2 or 3 years. Energy conservation, hopefully we can keep that, right? Like in molecular simulations, I think energy conservation, that hopefully that chip, we have thermostats, right? So that we'll put energy conservation over there with a hammer if we need to. About sort of the emergent, I think I'm mixing two arguments. One is sort of scaling laws have a fixed metric, and the y-axis and the x-axis are fixed, and you just climb up. And in the process of doing that, behaviors emerged that were unexpected. So we're combining two things, right? One is the scaling law where you measure, but we get our SSI bench, and we say, if we add, $100 million in compute, we're gonna be 10% better than a PhD. And if we add more compute, we're gonna X time better. How much will you pay for, what's the difference between the University of Salamanca and, University of Chicago PhD? So that premium, right? That you stack that. So that doesn't even need emergence. The emergence of hypothesis is that in the same place other folks saw emergence, we aspire to see emergence, but it's not a given, right? I think the scaling law and the emergence argument are separate. They're intertwined, but they're two different sort of metrics of performance.
And I'll just have a plug-in. So last SciFM, we had a 4-hour session and panel just on emergence, and it's on YouTube, so you should look it up. All right, one more question apparently before, very short question, short answer.
Sure.
Yeah.
I'm Aladdin from University of Michigan. So based on your weather models, from local weather model to global weather model, there's scale bridging issues. So as a material scientist, if I want to convert a DFT-based calculation, translate it to a device level, property predictions. So how we can learn from your experience that these physics-informed AI can help us in scale bridging?
Scale bridging.
Extremely tough.
Yeah.
This is actually extremely tough because all these models that are super successful, they're trained on the same scale that they're used at. And then if you want to do any other scale, it gets very, very, very hard. And there's, I cannot help you here.
Yeah, there's a turbulence button here. So
I think there is the topic of multi-scale modeling is something that has appeared in different fields. And then there is a lot of very interesting methods. There is, for example, the equation-free method of Kevrekidis. And if you look at the elements of the equation-free method, he used Runge-Kutta for time integration and some kind of interpolation. Now with machine learning, you can use recurrent neural nets or transformers to do the time integration, or you can use autoencoders to go down to the different scales. So I am very hopeful that for multi-scale modeling, AI and machine learning offer a lot of different tools, and it's a matter of becoming aware of the capabilities and limitations of these tools and bringing them into the particular problem that you are interested in. So For example, a particular example, I have been familiar with GraphCast, and GraphCast does something very, very interesting in the way they are processing the information from the grid of the Earth. In a sense, they're doing some kind of multi-scaling process of combining information from different domains. And if you capture the correct way of transferring the information, then you can be very much predictive. So you can look at GraphCast not only for the sake of how well it predicts the weather, but the methodologies in there, I think they can be transferable to other domains.
It's like any CNN.
So I think we got to wind up.
Like
And
any CNN.
last question from Ricardo, and then yeah, we got to wrap up.
Information theoretic.
Yeah.
Yeah. Multi-scale. This is He's talking upstream about observation retrieval. Okay, it says multiple resolutions. Oh yeah, no, that part is the same. Yes.
Ingredients that should be in our model, not everything, and not in a kind of discipline guided way, but more in a more objective data way, and then the models that just with essential ingredients that we can still
It's a long question. Yeah.
Again?
Yeah, you get last shot.
I think your compatriot Adrian Lozano Duran is working in this area, and he does some very interesting work where he tries to use information theory to look at how, for example, you can decide a priori what is the predictability of the certain system, or figure out what are the proper variables to describe a certain system. So I think it's a very very interesting way to look at that. I will have a provocative also answer that I think if we eventually will let agents talk to each other and we don't touch them, and we come back in the room after maybe a decade, I will not be surprised if some of these agents have not developed inductive bias that reflects physics, chemistry, and so on. But who knows? Maybe we need to see about that.
Yeah. All right. Maybe last response.
Yeah, maybe that's something that, like, connecting the two last two questions. But like in terms of like weather models, the fact that now we can see them, how they learn from dynamically similar events in other regions. It's actually something very interesting, unexpected, and they really focus on only dynamical similar events. They actually don't learn from things that we know from the physics that are different. And I think this is how, if you look at the full state vector, that's how they see the difference. But I think that's something about the regional versus the global scale. I think there was a paper earlier that they did a back of the envelope calculation that if you account for the speed of sound and the speed of Rossby waves, actually these models, like when you do a 6-hour forecast, like what is the size of this receptive field? They were arguing that it should be limited so the model don't learn, talk to other regions.
Right.
And it turned out to actually be a bad idea, right? So because I think the models work well, really because they can learn from other regions.
Okay, anyway, very good. Yeah, so I think, yeah, we should wrap up. I'll just say one thing. One topic we did not get into, maybe you talk about it during lunch or in the other panels, is societies of agents. So that's probably going to be a big topic for next SciFM, I feel. I have a feeling about that. But thank you for the panelists, though. Good.
So few logistics announcements. We'll have lunch outside for most people, but student meet and greet will be on 8:01. And to get your lunch, please move from the left-hand side, or my left-hand side, which is the right-hand side of the room. Get your lunch, and the students, please go to 8:01, and most people should be there along with the industry meet and greet.
I learned, so I think
Thank you. See you back at 1:30.
Thank you.